Hello students, welcome to EPG Pathshala. I am Dr. Varun Vyas from Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about the module Recorders and Recording System Part 2 from the paper Measurements and Instrumentation. In this module, we will study about modern digital systems. First, we will study about digital display devices, and then in detail we will look into magnetic recording systems, and finally we will look into few applications of the modern recording systems with biomedical applications, that is EEG and ECG. In this module, we continue to look into various recording devices that can store data long after the signal has ceased to exist. Earlier, we had discussed about graphic and oscillographic recorders. In the 21st century, most of the analog systems have been replaced by digital data recording and measurement systems. The main component in the most digital measurement system is an amplifier along with the feedback system to monitor range and frequency of the system under observation. Besides the recording setup in most digital systems, real-time monitoring of the measurement is equally important. This helps adjusting the parameters before one may start to record the data. At present, the most recording systems have a computer interface to monitor measurements. During early development of digital recording devices in late 20th century, real-time monitoring was done via digital display systems. Let us start with digital display and data recording system. Digital instruments. An analog instrument displays the quantity to be measured as deflection of a pointer, that is, an analog displacement or an angle corresponding to electrical quantity. Whereas a digital instrument indicates the value to be measured as a decimal number. A digital meter works on the principle of quantization, and in analog, measurable quantity is first subdivided or quantized into smaller intervals up to many decimal places. Here, the objective of the digital instrument is then to determine in which portion of the subdivision the measurement can thus be identified as an integral quantum multiple of the smallest unit called the quantum for the chosen subdivision. The reading accuracy can be further increased by increasing the number of decimal places, that is, by increasing the quantization levels. Advantages of digital displays. First, a reading indicated is in decimal numbers, therefore errors due to parallax and approximations are eliminated. Second, the reading can be carried out to any number of significant figures. Third, since the output is in digital form, it may be directly fed into the memory devices like tape, recorders, printers, or computers for storage and for future computations. Fourth, power required to operate digital instruments is considerably smaller. Digital display units. Digital devices can be broadly classified as planar and non-planar, based on whether the displayed characters are in the same plane or on different planes. The segmental display like LED, LCD, dot matrix displays, and segmented gas discharge displays are planar, whereas non-planar ones include Nixie tubes, gas discharge tubes. Example of segmented and a dot matrix array is shown in the figure 1. Dot matrix display are generally used to display alphanumeric characters. LED, that is a light emitting diode, is PN junction semiconductor device that gives light as output when current is fed in its forward bias configuration. A liquid crystal display, an LCD, is made up of liquid crystal cells which either transmits or reflect light. They do not generate light on their own, instead require an external source of light to produce an image. Both Nixie tubes and segmental gas discharge display work on the principle of gaseous discharge glow, where a discharge glow can be observed when the gas in the tube breaks down. Both types of gas discharge displays are built into 7 or 14 segments to display numeric or alphanumeric characters. Magnetic tape recorders. Recorders discussed until now are low frequency recorders, and it's not possible to retrieve or reproduce data in electrical signal form. With magnetic tape recorders, the recorded data or the information to be retrieved can be converted to electrical form again. It is possible to record data at much higher frequency of the order of megahertz. Plus, larger volume of data can be stored, and they also give fast access to stored data. Different types of recording systems like magnetic tapes, discs, strips, drums, or loops use the same kind of transducers and magnetic medium to record or reproduce the data. There are three methods to record data on magnetic tape. First is direct coding, second, frequency modulated recording, third, pulse duration modulation. But before we look into these three methods, let us discuss the basics of magnetic recording system. Construction. A magnetic tape recorder consists of magnetic tape, recording head, reproducing head, tape transport mechanism, and conditioning device such as amplifiers and filters. Figure 2 illustrates a simple magnetic recording system. Magnetic tape, it has plastic base which is typically polyvinyl chloride or polyethylene terephthalate, or for example mylar. This thin sheet of dimensionally stable plastic on one side is coated with a magnetic material. This magnetic coat consists of very small iron oxide particles mixed in a plastic binder. The needle-shaped iron oxide particles are about 0.6 micron long and 0.1 micron in diameter, occupying 50% of the coating volume and oriented in the direction of their long axis along the length of the tape. Next is recording head. It is a device that leaves a residual magnetic pattern in response to an amplified input signal. Its basic construction is shown in figure 3. It consists of a toroidal core of high permeability material with a coil and fine air gap of 10 micron. This air gap gets shunted by passing magnetic tape, and coil creates a flux of the similar shape to bridge the air gap. Iron oxide particles get magnetized when they leave this air gap, and so the actual recording takes place at the rear edge of the gap. Thus, the magnetic pattern that is spread along the tape is similar to the original coil current variation in time. Reproducing head. The design of the reproducing head is similar to the recording head. When the magnetic tape passes over the head, the resulting output voltage is proportional to the magnetic flux in the tape developed across the coil of the reproducing head. Thus, the magnetic pattern stored in the tape gets converted into original electrical signal by reproducing head. Next is transport mechanism. It moves the tape over the recording and reproducing head at a constant speed without any strain, distortion, or wear. This mechanism guides the tape near to the magnetic head with great precision and maintains proper tension during data recording or signal reproduction. Operating principle. When a magnetic flux is applied to the iron oxide particles in a tape and then removed, a residual flux is left behind. An earlier state of magnetization and the magnetization curve of the recording medium governs the relationship between the residual flux and the recording field. Typical magnetization curve for a single magnetic particle is shown in figure 4. Here one can observe relationship between magnetization force H and flux density B. A completely disgaussed material is at point O. As the current in the head increases, flux density in the direction of increasing magnetization force gets saturated at point C. This can be observed along the path OAC. In case the operating point is brought to point A and magnetization force H is brought to point 0, the flux density follows a hysteresis path to point K. Therefore, when large value of current passes through the coil, it will leave a higher magnetic flux and lower current will leave lower residual flux, but linearity between the flux and the current is poor due to hysteresis. To secure a linearity of the recording data, various techniques like direct method, frequency modulation, and pulse modulation are used. Now we will discuss various data recording methods. Direct method. This is the most economical and simple method for analog recording of the signal. A signal of a certain amplitude and frequency are linearly recorded as in the variation of the magnetization amplitude and wavelength of the tape. By adding the high frequency AC bias to the recording signal, one can get amplitude linearity when recording data. Through the coils, input voltages get converted into proportional current. A magnetic flux created at the recording gap is given by phi is equals to k phi into I. This is equation 1. With sinusoidal input signal, we get I is equals to I naught dot sine 2 pi ft. This is equation 2. And with the tape speed of V meters per second, the intensity of magnetization along the tape varies sinusoidally with distance x, as magnetization is given by m is equals to km dot k phi dot I naught dot sine 2 pi f into xv, where m is equals to km dot phi. The wavelength of the magnetization variation is then V divided by Fm. Thus, the resultant magnetic field in the recording gap enables magnetic recording as the tape passes under the gap. Direct recording is mainly employed for recording the speech and music as in sound recording, and the ear averages the amplitude variation errors. Frequency modulation recording. Input signal is modulated by a frequency modulator and is recorded linearly using AC bias or a non-linearly without bias on a magnetic tape. For reproduction, the recorded information is reconstructed by frequency demodulation and filtering. In this system, variation in frequency is used instead of amplitude for carrying desired information. This system is preferred when a more accurate recording and response to DC voltages are required. Pulse duration modulation recording. Here, input signal is converted into pulse, duration of which is proportional to the amplitude of the signal at that instant. For example, if sine wave is to be recorded, it is sampled and recorded at uniformly spaced discrete intervals. For playback, original sine is reconstructed by passing it through appropriate filter. It has a high signal to noise ratio, high accuracy, and information can be recorded from large number of channels. Its main drawback is use of highly complex circuitry, low reliability, and limited frequency response. EEG potentials are small in amplitude, therefore preamplifiers are used. Here, one must have high gains and low noise characteristics. Plus, the amplifier must have a very high common mode rejection to minimize any stray signal interference from power line or any other electrical equipment. EEG simultaneously records signal from any array of electrodes. Electrodes are separately connected to amplifiers and writing systems. A commercial setup can have up to 32 channels, though 8 or 16 channels are more easily available. Applications. There are number of applications of recording devices. We have discussed one such application where one can use magnetic heads to store data within the audible range by using magnetic tape recorders. Other application of recorders for biomedical applications are electroencephalograph (EEG) and electrocardiograph (ECG). Electrocardiograph. It is an instrument that records electrical activity of the heart. Electrical signal generated in the heart precedes the normal mechanical beat that distributes the blood throughout the body. These signals are of great clinical significance and are used for diagnosing wide range of cardiac disorders. The block diagram of ECG machine is illustrated in figure 6. The signals, that is potential picked from the patient electrodes, are taken to the lead selector switch. A lead program in the selector switch selects 2 by 2 electrodes. Via capacitive coupling, the signal is connected symmetrically to the long tail pair differential preamplifier. The single-ended output from the preamplifier is fed into power amplifier, which is usually of the push-pull differential type. The base of one transistor in the power amplifier is driven by unsymmetrical signal from preamplifier, whereas base of the other is driven by feedback signal resulting from the pen position that is connected via frequency selective network. The output from the power amplifier is fed to the pen motor, which deflects the writing arm of the paper. Cardiograms are recorded on graph paper with horizontal and vertical lines at 1 mm interval and thicker lines at 5 mm interval. For routine work, paper recording speed is 25 millimeters per second. Amplitude readings are recorded vertically in millivolts. The sensitivity is typically set at 10 mm per millivolt. Electroencephalograph. It is an instrument that records electrical activity of the brain. Electrodes for the measurement of electrical activity are placed on the surface of the scalp. The electrodes are small in size and are applied separately or mounted over special bands placed on the patient's head. Signal picked by surface electrodes are smaller than the signal picked by ECG. Their range is several hundred microvolts, but peak-to-peak voltage of 50 microvolt is often observed. Brain waves, unlike electrical measurements of heart, lack periodicity. That is, the same pattern is not repeated over and over again. Recordings are conducted over longer interval of time to detect any abnormalities. The block diagram of EEG machine is shown in figure 7. In this module, we studied about modern digital systems. First, we studied about digital display devices, and then in detail we looked into magnetic recording systems, and in the end we looked into few applications of modern recording systems with biomedical applications like EEG and ECG.